Hey, math people, lecture 8. We're almost there. We're at the little tail end here of all of our differentiation rules for differential calc 1. A little overview, we're going to build this idea called implicit differentiation. Show why it works. So up to you if you want to watch that. See it in practice, look at some of the applications of it, and then do some of the more technical cases toward the end. So remember, this video is for you, Carlos, or whatever your name is. The mantra being, use pause, right? And to use the timestamps to see what is most appropriate for you. That's math. Okay, so very Rene Descartes, I think, therefore I am, cogito ergo sum, if I'm saying that right, themed. So imagine you're Fermat and Descartes goes, I bet you can't find the tangent line to any curve at an arbitrary point. And Fermat's like, challenge accepted. These are just math people. You can ignore all that. Let's just do the following. If I had a circle, which I'll go ahead and graph, x squared plus y squared is equal to 25. You got this circle. This is not a function. So the motivation for this section being, what if I want to take the derivative of things that fail the vertical line test? Because if you think about every function we've done so far, sine of x, x squared, e to the x, all these functions pass what is known as the vertical line test. I can move a vertical line, something like x is equal to k. Nope. X is equal to r. Hello, n. Hello. I want to create a slider for this. N is equal to 2. Give me a sec here. Yeah, okay, look at this. Trust. Okay, there it is. If I run a vertical line through, I'm only in contact with the red line one time for each of these functions. Whereas, alas, I fail that concept within the circle. So, vertical line test. What I want to do is I want to come up with the slope of this expression at the point 3, -4. Right down here. So, I can estimate it. It looks like it's a slope of like 1 or something. Who knows? But I want to actually come up with it for real. So you can do this without the new process known as implicit differentiation by solving for y, creating it as a function. Remember, if you take the square root, you need the plus or minus. That's my hint if you're going to try this on your own. But go ahead, solve for y, and then plug in 3 into that expression, if that makes sense. But otherwise, we're going to go over it in 3, 2, 1. All right, so I isolated y. I took the square root, and that's where the plus or minus comes into play. If you didn't know, now you do. Y is equal to the square root of 25 minus x squared. That's the top half of this circle, and then the bottom half being just that negative piece. So we're looking at this, and this is now a function. It passes that vertical line test that I was demonstrating earlier. And what you could do with that expression is you could do the chain rule. Right, so already using the chain rule right away. The first problem in the lesson immediately after, that's how used that rule is. I rewrote the radical as power of 1/2, so then I wrote it up front. Negative was there, and then power is reduced to -1/2 now. Keep inner the same, and then derivative of inner is -2x. So it simplifies to this expression. And my guess was off. I guessed that it was a slope of like roughly 1. I don't know. It's close, right? It's a slope of 3/4. So if you plug in that 3, this is the expression that you end up getting. Okay, so this was too much work is the idea behind the fact that we had to solve for y, which sometimes you just literally can't. So sometimes you get a curve where it's not possible to solve for y. Here it just happened to have been somewhat possible. It just broken into 2 different functions. So is there a faster way? Heck yeah, there is. It's called implicit differentiation, and the way that works is you can just take the derivative right away. So we have that x squared plus y squared is equal to 25. Go for it. Let it rip. Get 2x for this one. But here's the thing. Y is a function of x. That's the way that we're observing this. Just like how we were able to solve for y here, create that function of x. That's the mantra or ideology that we're going to instow. Is that a word? Into taking these derivatives. So when I encounter y squared and I'm taking the derivative with respect to x, right? Y is known to be a function of x. This is like y of x here. So, all right, if you have a function, y of x inside of a function, the square, we need the chain rule. So the idea behind that is that 2 is up front. The inner function y stays the same. And then what is the derivative of y? It's dy dx, right? It's just strictly dy dx. I'm just applying d dx to that inner function y to get dy dx on the outside. So this is literally chain rule. That's all this is. This moment right here is the harder moment of the day. It's implicit differentiation. And what it is implicitly is the chain rule. That's funnily enough. All right, well anyway, now we can solve for dy dx, subtract the 2x onto the right side, divide out that 2y, the 2's cancel, and you get negative x over y. Well, we have the full point that we want to plug in to find the slope at, so the 3, negative 4, I just plug this into this expression, and alas, I get 3/4, which is the same result I got above. So implicit differentiation, it's a new move, it's an ideology, it's a vibe. No, it could say aura. It's an aura. It's not an aura. All right, go ahead and read this with me here. So this is just my soft way of saying, hey, this thing works. So up to you if you wanna join me. So if I have y and I know y is a function of x, it happens to be, say, 3x plus 5. If I'm taking the derivative of y squared, which would be 3x plus 5 all squared, here are the 3 ways we can do that. There's the no chain rule approach, which is, okay, I know that y is 3x plus 5, so just plug it on in, and I can just use algebra to multiply it out. I've done no calculus so far. I've done substitution and then foiling, or distribution of 2 binomials. And then I went ahead and I took the derivative of each term. I just did power rule, and I got 18x plus 30. The explicit chain rule way is to, do that substitution, write that square up front using the chain rule, keep inner the same, and then the derivative of the inner being 3. 2 times 3 is 6, distribute that in, hey, I also get 18x plus 30. The new way, so this is the new approach, is implicit differentiation. Don't do the substitution until the end, I suppose. But the idea being, okay, well, the innermost function is y, and the outermost is the square. So the 2 comes up front, inner stays the same. Derivative of inner is dy dx. Now I can do that substitution if I want to just simply verify that these are indeed the same thing. So y is the 3x plus 5. I subbed that in. The derivative, dy dx, of y is just 3. It's the slope, so I just plug that in. Hey, these look familiar. It's the same thing. So chain rule works and stuff is what we got from this. Implicit differentiation works and stuff. Chain rule works, implicit differentiation works. Calculus just works, man. But truly, try to unpack each of these steps. The idea is that you're building an intuitive and you piece together the image on your own rather than just someone telling you the rules. Okay, so go through the work if you need to. All right, ergo implicit differentiation. So let's go ahead and find the slope of the folium of Descartes. You guys know the folium of Descartes, x cubed plus y cubed is equal to 6xy, right? It's this expression right here. You didn't need to know that. I don't know why he named it that, but it's a thing. So I'm gonna go over this in 3. Okay, so what you wanna do, let me explain. Find the slope. So you wanna find dy dx, yeah? And then plug in 3, 3. And you'll get a number. So you're finding the slope at 3, 3. Before I show the answer, 3 is right here. So, think about what the slope might be. If it's kind of going, if I want to think about the tangent line at this point, it's kind of going like this. So I don't want to say it out loud because I want to give you the chance to explore. Anyway, give it a go. 3, 2, 1. All right, so I just went ahead, I took the derivative right away. Derivative of x cubed is 3x squared. Derivative of y cubed is, 3y squared, but remember y is a function of x, so times dy dx. And this is a little tricky. It's a little hard to see that this is actually this is a product rule right here. This is the quantity of 6x times y. So those are like 2 different functions, right? So if you have a function times a function, that requires product rule. So what I did was I kept the first, I took the derivative of the second plus derivative of the first, which is just 6, and then I kept the second, which is just y. So I did product rule here. Anyway, what I do next, I subtracted the 3x square onto the right side, and then I subtracted the 6x dy dx onto the left, and that's to clump my dy dx stuff on one side and then the other stuff on the other. This would enable me to factor out the dy dx. And by the way, I could have just plugged in 3 comma 3 right here and then just solved for dy dx as if it was a variable, but I'm looking for the derivative generally. So what I did was I moved all my dy dx stuff onto one side, anything without dy dx on the right. I factored out the dy dx, and then I divided out this expression to get this fraction right here. So now I can just plug in 3 comma 3, and then just whatever shoots out is the slope at that point, which happens to be -1 after doing some simplifying and plugging in stuff math. And you get slope of -1, which kind of matches your intuition of like, yeah, it looks like it was like down 1, right 1 at this point, and it is. Go math. Yeah, so let's do some more. Yeah, okay, so here's a equation that I hope you know what it looks like. Something squared plus something squared is equal to a number. It's a circle. Find the horizontal and vertical tangents. What? All right, well, okay, let's talk about this intuitively first. Intuitively. So if I were to graph a circle, hopefully you know this. What's the knowledge that you're coming in at? Like, I was like, really hope you know what this is. And then I'll just do r squared just for the sake of the whole story. So yeah, like this is the general equation of a circle. H does left, right, K does up, down, R does bigger, smaller, radius. Right, this is just like a Pythagorean theorem, sort of just all the way around in a 360. Yeah, like I said, your horizontal shifts, your vertical, and then your radius. So I'm just gonna go ahead and scoot this on over to 3. There it is. No. I'm not gonna do it this way. Because if I were to make h a 3, it would be x minus 3, and that's not what I want. I'm going to just go ahead and graph it now. So that would be 3 to the left. This would be 2 down. And then my radius was just 1, right? Oops. Ignore all that. There it is. Yeah, so that's what's going on here. This graph is this. So it's 3 to the left, and then it's 2 up. Yeah, 2 up. Sorry, because it's y minus k. So k was positive 2, so it's 2 up. And then the radius is just 1. Okay, so let's think about this through the language of horizontal tangents and vertical tangents. Horizontal and vertical tangents. Horizontal tangent is when your slope is horizontal. Vertical tangent is when your slope is vertical. So looking at this circle, how many times does it appear? I mean, you can actually just find the points. They're natural numbers, so they're easy to find. How many times does the slope kind of just flatline for just an instant, right? Instantaneous rate of change. And then how many times does the slope go totally vertical, right? You can actually find the ordered pairs quite quickly. I'm not going to click them. I'm not going to say them. So this is where the math gets like fun, in my opinion. See if you can verify it using implicit differentiation. So I'm going to pull this away. You could do this in one of 2 ways or both. Find them on this graph, so you can pause right now and then just get those ordered pair solutions. Or you can just use implicit differentiation and then set something to some number. Horizontal tangent, what's your slope when you're horizontal? What number might that be? All right, anyway, I'm going to go over it now. 3, 2, 1. Whoops. Okay, yeah, the answers are here. But if we're going to just work through the implicit differentiation approach, what we're doing is we're doing the derivative of this expression, which is like a chain rule right away. So I'm doing the 2 up front, keep inner the same. Derivative of inner is just 1, so we're just moving along. Likewise, 2 up front, derivative of inner, y minus 2. The derivative of y is a function of x, is dy dx. And then derivative of a constant 1 is just 0. I divided out those 2's because they're annoying. Get them out of here. And then I subtracted over the x plus 3 onto the right side, and I divided out the y minus 2. So I solved for this dy dx using algebra. Well, anyway, I get this expression, and let's think about it. If I want to find when I have horizontal tangents, that is a 0 slope, no slope, flat slope. So I'm just setting the top to 0, the numerator to 0. And then I'm solving, I'm solving this equation, which is easy to solve. Just divide out the negative, subtract the 3. You get x is equal to -3. Okay, but remember the answer is, it's saying where, which is like an ordered pair. So I need to plug that -3 back into the original equation and solve for y, which is not that bad. You just have to be mindful. If I'm taking the square root, I have the plus or minus of 1. Then I'm adding that 2. So I'm getting, for y, I'm getting 2 answers out of this. 2 plus 1 is 3. 2 minus 1 is 1. I'm getting -3, 3, and -3, 1. Let's take a look at that. So, where do I have a slope that flatlines? Hopefully you're with me here. It's at this point and at this point, which, would you look at that, are the same 2 answers over here. So, if you didn't do the first one, maybe try to do the second piece, the vertical tangents, with me right now. If we're thinking about vertical slope, that's like an undefined wall slope. So give that one a go. Hopefully you didn't study blue too much. You're setting the denominator equal to 0 this time instead of the numerator equal to 0. So I'm going to go ahead and explain it right now, though. So denominator equal to 0, I'm getting y is equal to 2, and I'm plugging that 2 into this equation. That nulls out. I'm just figuring out when this first term is equal to 1. So I'm taking the square root, there's your plus or minus, and then I'm getting 2 solutions. Here are those points. So when I'm looking at the vertical slopes here, there are 2 instances where that happen. The first one being at -4, 2, which is listed, and then we work our way to the right side, and that's at -2, 2. It's nice how Desmos just snaps onto that for me. That's very kind of you. Desmos just added inference, by the way, a lot of stat stuff. I don't know, that's aging this video probably, but oh well. Love Desmos. All right, so yeah, that's it for these two. So we had two vertical tangent moments and 2 horizontal tangent moments. So if I were to like define that, really, it's just take your dy dx, set your numerator equal to 0 for your horizontal tangents, set your denominator equal to 0 for your vertical tangents. You just have to be mindful. I did kind of hand wave over it. You don't want the case of 0 over 0. That is not necessarily a horizontal or vertical tangent, and actually, like, just be mindful, 0 over 0 is not going to render these scenarios. All right, so more practice if you like. Just simply find the derivative. This is maybe what you're looking for. Just find dy dx when you're given kind of just random implicit curves that are not necessarily functions. So 3, 2, 1, give them a go. Oh, yeah, so I found dy dx. Derivative x is 1. I did all this right here is a product rule of this expression, right? 2x squared times y cubed. So I did a product rule. There's your implicit differentiation moment right there with that y. And then with the second term, 4y squared, that would just be this derivative right here. Bringing that 2 up front, you get the 8, keep inner the same, and then derivative of y is dy dx. By the way, I'm using dy dx. I'm writing that a lot. Your teacher might have had you wrote y prime for each of these moments, which is totally fine. My only issue with that is that, 1, if you're going to continue with calculus, Leibniz notation is just the way to go. And 2, I'm setting up for something I have in mind. Eventually, you're going to cover what's called related rates. And instead of taking the derivative of x on the outside, you're taking the derivative with respect to a different variable. I just simply want to get you prepared for that moment. That's all. So if you're writing y primes, that's totally fine. Anyway, what I did here thereafter was I moved all my non-dx dy gunk onto the left side, and then anything with dy dx, I kept it on the right. I factored out that dy dx, and then I divided by the coefficient of it. I divided by this binomial here onto the other side. So I isolated dy dx by moving all the dy dx gunk onto one side. The other side doesn't have it. Factor out the dy dx. You always do this, by the way. And then divide by whatever is being multiplied by the derivative. You can see I even do it over here. So I did product to start, and then I just did basic derivative for x, and then I just did implicit for the second term. Moved all my dy dx gunk onto the left side, anything else without it on the right. Factored out the dy dx, here's that move again, and then divided out the binomial, so you get this expression. By the way, another little for fun asterisk here is that you may get the answer like -6x plus 3y cubed minus 9xy squared minus 3y squared. That might happen, and the reason why, if you take the fraction, say like 1/3, consider -1 over -3. Those are the same things, right? So a negative over a negative is a positive. It's because of that. You can like factor out a negative, factor out a negative. So don't panic, don't freak out if your answer is like the exact opposite answer, like everything's, all the signs are different. No, it's probably just because of that. All right, another round, 3, 2, 1. Okay, you can read through this one as you see fit, but I'm just gonna highlight the big picture. I'm starting with a product rule, and then you have an implicit on the inside. Derivative of +2 is just 0. And then we got the implicit here. Whoa, that's a mess. So I just did the same stuff, though. I moved all my dy dx stuff onto the right side. That enabled me to factor it out and then divide out by what remains, the 2y plus x sine x plus y, which is the denominator there. And then I'm isolating that dy dx. Guess what? The same thing happens over here. So I did view this as a chain rule. So I did e to the blah is e to the blah, and then I did the inner function being xy, and then that's that's kind of interesting. It's an implicit inside of a product inside of a chain. So this is, I don't mean to like hand wave over this quickly. I'm just trying to make this video, some sake of brevity for it. But this is a little involved. What I did was, so one last time, derivative e to the blah is e to the blah. Then I did the product rule. Derivative of x times y, and then when I encountered that y, when I took the derivative of it, it's dy dx. Derivative of 2x is 2, and then derivative of 2y is 2 dy dx. And I did the same stuff. I moved all my non-dy dx stuff onto the right side, factored out that dy dx, and then divided out by what remains next to that dy dx. All right, some practice finding vertical and horizontal tangents. Give it a go. 3, 2, 1. Here it is. So you take the derivative, you get a fraction, and then you set the numerator equal to 0 to find the horizontal tangents. You set the denominator equal to 0 to find the vertical. So within the first one here, you can't set 1 equal to 0. It just doesn't happen. But we do have a vertical tangent. If you set that denominator equal to 0, you get 1, and you can plug that in to find an x value of 4. And it's just fun to like kind of sometimes show these. I'll just show this one. I'm not going to show the second one. But if I graph it on a Desmos, it's nice to see that the answer just works. It just matches what you see graphically, because here's that vertical tangent at 4, 1. It's just a sideways parabola. We get a mess of a problem for this one, but it's still the same philosophy, setting that numerator equal to 0. You get one of your two coordinates, and then you're plugging in to find into the original equation to find the second component of it. So we have 2 horizontal tangents and 2 vertical tangents. My guess is that this is like maybe an ellipse or something. I don't know. Go ahead and graph it if you want. All right, man, this one's a little longer today. We do need to talk about the second derivative. So these are a little bit different. My hint being, when you encounter within the second derivative a dy dx, know that you already found it. You already solved for it. So you might have to do some weird kind of substitution. If you don't like that, just wait for me. 3, 2, 1. All right, so I take the derivative here. I get dy dx is equal to negative x over y. We did this derivative earlier. We did it for a different circle, but negative x over y looks familiar. When I take the derivative here using the quotient rule, you can see here that I get this expression, and then when I find that y, the derivative of y, it's dy dx. Hello? I already know what dy dx is. It's negative x over y, so I just sub it back on in. And then I can simplify it up, clean it up that way. Same story over here. It's just another quotient after taking the first derivative. And then I took that, and I picked it up, and I placed it back down when I encountered dy dx within the second derivative. Fun. So second derivative with implicit differentiation. Last one. Let's try to keep this under 25. When we have like non-differentiable moments. So this is more of like a bonus round kind of thing. So give it a go. Find when we're non-differential, take the derivative of this expression, and then see if you know what to do next. 3, 2, 1. I went ahead, I found the derivative of this expression, and it's this thing. Whoa, what a mess. What you can do is, I don't know why I wrote it like this. That was so weird of me. That is so weird of me. Okay, to illustrate that you have like these bad guy moments. But I think there was another way of me showing that. You really just get the cube root of y over the cube root of x. And, well, 0 is the bad guy number when you write it this way. You can't have an undefined here. You can't have an undefined here. And if you were to look for those moments by plugging that 0 into the original equation, you get all 4 of these, which are all cusps. So Yeah, go math. Look for those non-differentiables. That's it for now. Math on.